This is Dr. Plank, day before Thanksgiving, and I promised that I would make a video to go over some of these recursion examples. So here it is. So, to play along, go to the lecture notes, go to recursion, and then I have some practice material here. And in particular, I have these 3 LeetCode problems that you can use to practice recursion. Now what I'm going to do is I'm going to go through all 3 of them here live. I haven't thought about them in a few days, and we'll go over these guys and go over their solutions. Okay, so we'll just start here with this one, power of 2. So, pause and read the problem description, but basically the idea is you're going to get an integer n here, and you have to decide whether or not it's a power of 2. Now, if I were doing this on my own, without recursion, it wouldn't be very hard, right? You can take the number mod 2, and first start off, if the number's 1, you're done. Otherwise, take the number mod 2, and if it is 1 mod 2, then since it's not 1, you know it can't be a power of 2, so you'd return false, and then just right shift it 1 and go ahead and do that. In fact, we can do that. It's probably not a bad solution to do to start off with. So here, you can say while 1. Well, first, we've got to look at the constraints. Okay, so we get negative numbers. True if it's a power of 2, no negative number is going to be a power of 2. So let's just start off with if n is less than or equal to 0, then return false. Otherwise, we'll do a while 1. And what we can do here is we'll say if n equals 1, then return true. If n mod 2 equals 1, then return false, because that means it doesn't equal 1, but it's an odd number, so it can't possibly be a power of 2. Otherwise, you right shift it by 1. You could just divide it by 2. It would be the same thing. And keep going, and you're done. Here, let's run that one. See what it says. Okay, got my test cases right. Submit. Why not? Going to work. It works, and it's faster than everyone because it's a great solution. Okay, but what we can do now is we can take this solution and turn it into recursion. That's the part that you're having a hard time with. So we'll do the same thing in the beginning case, right? We'll go ahead and start off if n is less than or equal to 0, return false. And then, now we're going to do a base case. We're going to do a very similar thing. We're going to test to see if the number is 1. If it is 1, we're going to return true, because 1 is a power of 2. So here, let's just do that. That'll be our base case. If n equals 1, return true. Otherwise, instead of putting this in a while loop, we can do it recursively. We can say, all right, let's divide n by 2, or right shift it by 1, either way, and call it recursively. Okay, and then that will do the exact same thing. Well, actually, no, that's not true. I'm sorry. We do the similar thing. We say if n mod 2 is equal to 1, then we return false. All right. Now we're good. Okay, so if it was odd and it wasn't 1, then it can't be a power of 2. Otherwise, now we're going to divide it by 2 and test again. Right, because if we've gotten to this part, it is a factor of 2, right? It's an even number. So we're just going to get rid of that even part by dividing by 2. So we can say return is power of 2, there we go, and divided by 2. Done. We will test. It's good. Submit. It will be slower. We still beat everyone because we're great. Okay, now if you need just a little more example, right, just let's think of an example. Like, let's say n is 28, right? 28 is definitely not a power of 2. How does that work? 28 is what? It's going to be 16 plus 12, right? So in binary, that's going to be 16 plus 12. 12 is 1, 1, 0, 0. 16 is a 1. So that's what it's going to look like in binary, okay? And so basically what we're doing is we're testing this bit, the rightmost bit. If it's 1, it's false. If not, then we're just going to divide by 2, try again, right? If that's 1, false, nope. If not, divide by 2, try again. And then here we go. That one is even, but it's not 1, so we return false. And indeed, that's not a power of 2. Okay, so that's a nice, simple recursion that you don't need to do recursively, but I think it helps you think about the recursion by doing it not recursively and then seeing how the recursive solution works. All right, we're going to try the second one. And this is of the ilk that you all hate, but these are really good LeetCode problems to do because they give you practice, in this case, with both recursion and with linked lists. Okay, now let's walk through the way they define a list. I don't typically use this construct in C++, but some people do. Clearly at LeetCode they do. So what's going on here is they're defining, it's a struct, same thing as a class really, called list node. It has a value, which is an integer, and then it has a pointer to the next node in the list. So this is a way that singly linked lists work. It's very much like the queue in our lecture notes. So the first node will have a pointer, next will point to the next node, etc., etc. The very last one's its next pointer is gonna be null or null pointer again. You can use either. True purists like to use null pointer, so we'll use null pointer because that's what LeetCode is using. Okay, and then this is the part that might be confusing to you. There are three constructors. Okay, the first one, if you call it with a constructor with nothing, then it's going to set val equal to 0, and it's going to set next equal to the null pointer, so it creates a single node list whose val is 0. You can do a very similar thing if you call it with an integer, then it's going to set val of that integer, but it'll still be empty. And then lastly, you can call the constructor with the value and with a list, and then what it's going to do is it's going to go ahead and it's going to create a new list that has this value at the head, and this list will be starting right after that. Okay, so it's good practice for you to write your own testing program with this, and I'm going to do it just so you can see how it's done. All right, so here, let's go ahead and grab ourselves a window here, junk.cpp. Look at all that stuff. Okay, we'll put that in here. Here, let's also get a bunch of includes. Never hurts to have that file sitting there in your back pocket. Okay, let's ignore this for now. Well, no, here. Let's just go ahead and we'll say return null pointer, null pointer. Okay, because we're not going to implement the method yet. I want to implement a main, and what I'm going to do with the main is I'm going to have it read in a whole bunch of integers. Well, here, in main, and I'm going to read them into a vector. So vector int, call it v. Int n, while cn goes to n, v dot pushback n. Okay, so I've created a list, or a vector, and now what I'm going to do is I'm just going to create a list from the vector, okay? And what I'm going to do is I'm going to do it in, you could do it in a couple ways. I'm just going to do it in backwards order. Okay, so I'll say list node star, let's call it rest and L. And so now what I'll do is I'm going to go backwards. I'll go backwards through my vector. So for I equals v dot size minus 1, I is greater than or equal to 0, I minus 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 minus. Okay, and now what I'm going to do is I'm going to use their constructor to create my list L. So I'm going to say L equals new list node v of I, because that's my value, and rest. And I'm going to set rest equal to null pointer to start with. Okay, so that's going to create a new list node with v sub I is the val, and then rest is going to be the rest of the list. And then when I'm done with that, I'm going to set rest equal to L, and that way, right now I'm just basically building the list backwards, and when I'm done, I'll have the list in forward motion. So when we're done, let's go ahead and print out the list. So we'll say for, here, let's give ourselves an induction variable, x. Let's say for x equals L, x does not equal null pointer, null pointer, x equals x next, printf %d with a space, x val, and then at the end we'll print a new line, return 0. See, we're not even calling this solution yet. Yeah, we're not, oh, that's okay. We're actually defining everything. We're good. Here, I'll make this big for you. Okay, compile. Is it a good day? It is not a good day. Use of undeclared identifier L. Oh, nice. I forgot to get rid of the comments. Okay. Gotta actually define it. Alright, there we go. Use of undeclared identifier null pointer. What on earth do you think I need to do with that? Where is null pointer defined? See, if you just use null, life is easy. What include file is null pointer and but it's keyword. Oh, it's in C++11. God, life can be so miserable, can't it? Okay, fine. G++ standard equals C++11. I think I only need one hyphen. Junk.c++. Uh-oh, forgot I. Okay. Just so I can't ever not teach, can I? Don't want to make I a size t. Why? Because then this will never be false. So I just made it an int. We're all good. All right, it compiled. So here, echo 1, 2, 3, 4 into a.out. Good. We get the list 1, 2, 3, 4. Okay, if that's confusing to you, go over this video slowly because that is just like creating a queue. And it's, as I said, great practice with linked lists. All right, now the LeetCode problem itself, which is this one. Okay, go ahead and take a quick read. Basically what it says is we are going to implement this method reverse list, which is going to reverse this list. It's going to take a linked list and reverse it, return the reverse list, and you're not supposed to allocate anything new. You are supposed to do this. I mean, I guess you could. I mean, so sorry, I'm like not finishing a sentence. It'd be very easy to implement this exactly like I just implemented this, right? You could traverse the list, put everything into a vector, take the vector, go backwards, actually take the vector, go forwards, and construct a new list, and you're done. However, what we really want to do here is we want to do this so we're not creating any new nodes. And so we're also want to get practice with recursion. So here's how we're going to do this recursively. What we're going to do is we're going to first, okay, take a base case. What is the base case? My list has one element. If that's the case, my list is already reversed, I'll return it. Okay, so here, let's go ahead and, all right, so now what we're going to do here is we will say L equals, we need a solution class, solution S, L equals S dot reverse list L, and then that'll print it out. We're all good. Okay, so base case, if head equals null pointer, that's the first one. Right, if the list is completely empty, or head next equals null pointer, meaning the list has just one node in it, then we're going to return head because we're done. Okay? Now, again, recursion. So now we know we have at least more than one node. So what we're going to do is we are going to recursively call this on the second node on the list. When I'm done, I'll have that list, it'll be here, I'll have that list completely reversed, and now what I need to do is I need to put this first node on the end. Now here's the great thing. To put the first node at the end, if we want to put 1 at the end of 2, when we're done with the recursion, we're going to have a pointer to 5, okay? because our list will be reversed and we'll get it in a return value. If we retain a pointer to 2, then we can just set 2 arrow next equal to 1, and then we're done. Okay? Let's write the code. We've had our base case, so now let's get ourselves some temporary pointers. Oh, and I said I never do this, didn't I? Implement something in here? It's disgusting. So let's not do it. There we go. There we go. Reverse list solution. All right. There we go. I guess we need to define this. That's good. Done, 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 done. Okay, there. Again, as God intended. Now we're all good. Okay, so let's get ourselves a couple pointers. Our first one, let's have it be to the second node. So here we go. List node star SN for second node. Let's have list node star RV for return value. Okay, and now we're going to set second node equal to head arrow next. Okay, so that in this case we're going to have head pointing to 1 and second node pointing to 2. Now we'll say RV equals reverse list SN, right? The list starting with this node, so that's going to reverse these. Now we're going to have a reversed list sitting in RV, but SN is still pointing to the 2. Okay. So now we can say SN arrow next equals the first node, which is going to be head. And then we're going to return RV. Okay. Again, that reverses everything but the first node. Now I pop the first node on the end. Now is that good? Is that going to get everything for us? We got to think to ourselves, what happens if this is just one node? If this is just one node, it'll return to it, and then we ought to be able to set next equal to head. I think we're good. Let's try it. Oh, figures. Oh. There we go. Okay. Echo 1, 2, 3 into A dot out. Well, that didn't work, did it? Oh. Okay. Oh. Okay. Oh, I know what I did. Good to look. So I got a nice little infinite loop looking like I'm going on here, and the reason is because when I've done this, you'll note I never did anything to head arrow next. All right, so head was just pointing to the second node again. So that's why we had an infinite loop. So here, head next equals null pointer. All right, we're all good. Echo into A dot out. Did that reverse it? It did. We're beautiful. Are we ready to submit? Of course we are. So here we go. Let's go ahead and do that. Copy and paste that. Pop it into here. It's going to compile. All right, they all work. Submit. There we go. We're faster than everyone because we are awesome. Okay, that was the second problem. I'm going to do a fourth problem, which is very similar to the second problem, a little trickier. Now, but before that, I'm going to do the third problem that I have in that HTML file. And this one is harder than the others, in my opinion. Okay, so they're playing a game. You have a string word called A, and then you're given this integer K. And now perform the following forever. Generate a new string by changing each character in the word to its next character in the English alphabet and append it to the original word. Okay, so here. So it'll start with A, and then in the next iteration it's going to be AB, because we're going to append A to A, but then we increment every character by 1. Next one's going to be AB, B, C, right? Because, I mean, here, we're going to do AB, AB, and then we're going to increment each of these by 1, so BC, right? And then we're going to do it again. We're going to increment each of these by 1, so B, C, C, D. All right, here, let's do it one more time. B, C, C, D, C, D, D, E. Hope that's right. Okay, and then your goal is to return the ith character. So you're going to get a character K. You want to return the kth character. It's 1 index because whoever wrote this problem's a moron. Okay, tripped me up in the beginning. So it's 1 index. So if you say 1, it's going to be A. If you say 2, it's going to be B. 3 will be B. 4 will be C. 5 will be B, etc., etc., etc. Okay? We can make sure we are right. 5 should be B. That was right. And then 1, 2, 3, 4, 5. That should be C. So that's that example. All right, we're good. Now, leak code wise, your constraints are that K goes from 1 to 500. So you could clearly just build this. You could build it and return it, and then you would be done and happy. Okay, but this is a problem you can also solve with recursion. Now, one thing to notice, right, is that no matter how big the word, the ith character is always the same, right? Character 5 is always going to be a B, regardless of if we keep playing the game and making this word bigger and bigger and bigger. Okay, so that's one thing to notice. Okay, the second thing to notice is, obviously, if you're going to know the ith character, then the word needs to be big enough to hold the ith character. Well, what's the smallest the word can be and do that? It's going to be a power of 2, right? 1, if you look at the length, 1, 2, 4, 8, 16. Okay, we're good. So what that means is, for example, when I is 10, that means we need the word to be 16 characters. Okay? Now, another thing to notice, because we're doing recursion now, and again, let's not think about the base case quite yet. Okay? With recursion, okay, when we're looking for I of 10, and we know that the word needs to be 16 characters, okay, then we know that the 10th character is in the second half of the word, which means we created it. If we know our word is 16 characters, and we're looking for the 10th character, which is this one, we know we could build it from the one before it, which only had 8 characters. And what we'll do is let's look back 8 characters, 1, 2, 3, 4, 5, 6, 7, 8, and add 1 to it, and that's going to be our answer. Okay? So, similarly, if it was 15, again, 1 index instead of 0 index is 15, then that's going to be the same as in the previous, but look 8 characters before. So 1, 2, 3, 4, 5, 6, 7, 8. See, it's a C. Add 1 to it, it's a D. Okay, so we're getting there. Now, our recursion, it doesn't have to be this way, but it's a lot easier this way. We're going to use 2 parameters. Okay, the first one is going to be I, which is the index we're looking for. And the second one is going to be W, which is going to be the length of the string that we're looking in. Now, we're never building this string, okay? We're just using it for the recursion. So, for example, in this one, when we're looking for character I, we would call this initially, what do we call it? Let's call it KC for kth character. So, int I, int W. Okay. In this one, we would be calling it with K, we'd be calling it KC of, in the example where it's 10, 10, 16, because we have a word of length 16 and we're looking for the 10th character. Okay? When we call this, we're going to guarantee that k is less than or equal to w. Okay, so we're always going to be looking for it in a word that's big enough. Okay, now let's look at two cases. Okay, first one is the one I just talked about, which is if I is in the second half of the word, which means that I is greater than w over 2. Okay, think about that. All right, if I is 10, it's in the second half of our word. If our word is of length 16, then characters 9 through 16, indices 9 through 16 are in the second half, and 1 through 8. Again, it's one indexed. 1 through 8 are going to be in the first half of the word. Okay? So if I is in the second half of the word, the answer will be kc of I minus w over 2, right? If it's 16, we're going to back up half. And then the word size is also going to be w over 2. Actually, it doesn't have to be. It could just be w. Let's just do it that way, actually. We're going to start it that way. Okay? So the answer is going to be that. So that's what we did here. We said we want to find this one. It's going to be this one, back up 8. That one plus 1, which is C. So here, plus 1. And then, wrapping around. So Z goes to A. Okay. So that means we have a second case. If I is in the first half of the word, let's misspell that, which is going to be I is less than or equal to w over 2. Okay. Now, what that means is, so if we're looking back here, if I is in any of these, we can chop off the second half of the word, right? Because it's going to be in the previous word. So the answer will be kc of I and w over 2. Okay, so you'll notice what we're doing in each recursive case is we are making I or w smaller. Okay, because that way is how we solve the problems. But we keep making them smaller and smaller and smaller, and then we're going to have a base case which is small. So base case is going to be I equals 1. If I equals 1, then return A. Right? Now you might say, well, what about W, Dr. Plank? Well, W doesn't matter because if I equals 1, regardless of the size of W, the answer is going to be A. Okay? And so, yeah, it's good because we're going to be making W smaller. That'll help us figure out these two cases. But eventually, right, we're going to keep subtracting values from I until it'll eventually equal 1. Now you might ask, could it ever equal 0? And it's a very good question to ask. If you think about it and look at the math, the answer is going to be no. Because look here, right? The smallest value you could have that you would actually subtract would be 9. 9 minus 8 is 1. Okay? And for the first half of the word, we don't subtract anything from I. So we're all good. Okay. So let's write the code. We've got it. Okay? Should we just write it live inside LeetCode? Sure, why not? Oh, actually, before we do that, that's all good. So now the initial call, for the initial call, we need to find the smallest power of 2, W, such that W is greater than or equal to I. Right? Because we're going to keep, we need to keep doubling this value until it's big enough to encompass where that index is going to be. Okay, so we'll do that here. So here, let's go with int W. They're calling it K. Okay, that's fine. Hey, we've been calling it I all along. We'll call it I. All right, so now here, let's find that biggest value of W. So for W equals 1, W is less than I. W times equals 2. Just so offensive to me here. Left shift equals 1. Done. Don't have to do anything inside of it. Now we're good. We've got W should be bigger than I. Now we're going to make this recursive call. So return KC of I and W. hate these editors. Just give me vim. All right, so now all we need to do is implement KC. Well, KC could be a method here of solution if we want. Frankly, it could just be its own procedure. You can do anything you want. I'm going to make it its own procedure just because I'm like that. So here, char KC int I int W. And now let's just walk through all the cases. For base case, if I equals 1, return A. If I is less than or equal to W over 2. Okay, right, so when W is 16, it's I is going to be in the first half if it's 1 to 8. So that's less than or equal to. Then we're going to return KC of I and W over 2. I don't know how anyone uses these editors. Okay, sorry, I didn't do that. There we go. Okay, so now we're in the final case, and this is the case where we're in the second half of the word. So here, let's give ourselves a extra variable. We'll call it RV for return value, and we'll say, oh, I see, that's where that is. There we go. RV equals KC of I minus W over 2 and W. Frankly, it could be W over 2 if you want, but I'm just going to do that because it'll divide it out later. Then we're going to return RV plus 1. So RV plus plus, if RV equals Z plus 1, RV equals A. Right, we wrap it around. Done. Return RV. And I think we're good. Going to compile? All right. Got that case right. Got that case right. Submit. Boom. And we're fast, even though we use that sloppy recursive solution. Okay, but I'm guessing we're faster than if we built up the word. Because we built up the word. If we built up the word, then we're burning some memory. I don't know. Y'all want to build up the word? See how it works? See if it works that way? Let's just do it. Here we go. We can say, what are we going to do? Let's build up the word. We'll say string W equals A. Now we'll say while I is greater than W dot size. Okay, well, then we need to build up the word. So now what we'll do is we can say, oh, this code blows. Let's get ourselves an int. Okay, int J. We'll say J equals W dot size. And now we'll go ahead and append W to itself. So W equals W plus W. And now we'll take the second half and increment every character by 1. So for nothing, J is less than W dot size. J plus plus W of J equals, well, let's just do what we did before. Here we'll go and we'll do W of J plus plus if W of J equals Z plus 1, then W of J equals A. And then when we're done, okay, and we're done, now we can say return W of I minus 1. Right, because W is going to be 0 indexed and I is 1 indexed. Does that work? Oh, closing brace. On line 1. Oh, try it again. My neighbor's mowing his lawn. Does he mow his lawn like every day? I think he does. Absolutely freaking nuts. There we go. See, it's slower than everyone else because that solution burns a whole bunch of memory. I honestly can't believe he's mowing his lawn right now. It's a freaking beautiful day. Why would you waste that? Never mind. It probably won't come across on the video. Hopefully, if it does, I apologize. All right, let's do the last problem, shall we? This is a bonus problem, so I don't really need to do it, do I? It's much like the first reversing problem, only it's got a little bit of trickier stuff in it. So we have a linked list, same thing, and then we're going to have a number k. And what k is going to do is k is going to say we're going to group our nodes into a group of k, and then we're just going to reverse those k nodes, and then we're going to move on and do it to the next k nodes. Honestly, I have to stop the video. Thank you, neighbor.